thickness of the limb, it can be classified or it can be differentiated into three types. First one is the parallel fold. This is the parallel fold, where these folds are also sometimes known as the concentric folds. In this case, you will be seeing some semicircles. So the limbs are made up of semicircles, okay, which has a center. So this could be the center of that. And one more thing, so when I am talking about the classification, one thing you have to remember, so what are the differences between two types? If you remember that, if you remember the key point, then you will be remembering the structure, or you will be remembering the entire thing. So the key point should be mentioned whenever you are writing in your exam, or in any competitive exam. If you are writing this, you have to mention it, the key points. Like here, you will be seeing some semicircular structure. Another thing, you will be seeing the thickness of the limb, which is not varying, which is constant throughout the area or throughout the folded structure. Okay, so you will be seeing the semicircles which have a constant center and a regularly increasing radius. You will be seeing that. So by seeing this structure, you can easily understand that the anticlinal bend for this section, let's talk about this section, and in this section the anticlinal bend is more sharper than the top portion. So if you move from this to this, okay, so at the top you will be having a wider zone or wider area comparing to the deeper locations. Okay, so similarly for the synclinal, what will happen? It will become broader with the depth but sharper upwards. So what type of fold is this? This section, suppose you are seeing only this section, not this one. So what type of fold is this? So what you can see is an anticline. Okay, it's a symmetric fold. Is it a symmetric fold or asymmetric fold? It's a symmetric fold. Yes, and along with this you will be seeing this is a parallel fold. So this is how you will characterize any fold. By stating these terms, I can understand. So okay, so this fold will look like this. So the in case of parallel fold, two things happen. That's have a constant center, okay, and the thickness will be constant throughout the area. Thickness of any layer will be constant. Another type of fold of classification you can consider, that is the similar fold. So in this case, the shape of the folds may vary. In this case, the shape will be varying. Whatever the shape will be, the shape will be varying. Okay, and at right angle, varying along the axial plane and also at the right angle of the axial plane. Both sides the shape will be varying, and here every bed is thinner in the limbs portion. So here you can see that at the limb portion the bed is thinner and thicker at the hinge portion. So and in the hinge area the bed will be thicker near the hinge and bed will be thinner throughout the limbs. Okay, so for this there must be a considerable plastic movement of material away from the limbs, which is, so plastic, what happened here, the plastic material will moving from this portion and it will be depositing this point. So considering the thickness of the limb, we can classify parallel fold and similar fold. So what type of fold is this? If I take this cross section, or if I take this section, so this fold is your anticlinal first, and this will be symmetric, and it's a similar fold. Okay, this is how I will be mentioning any fold. Now another type of case you may observe, and you may classify a fold with the basis of thickness of the limb. There is another type, there is a third type, that is called the supertenuous fold. So in case of supertenuous fold, what happened, it's sometimes called the compaction folds. So see this reef structure, remember, so it's a mound like structure. It's a pre-existing structure, generally is thought to be the result of wrapping of sediment layers by differential compaction. I'm coming to that. So how this is formed, first let me explain the supertenuous fold. Suppose there is a mound like structure on earth surface. This is the mound like structure, or this is called reef. Now sediment depositions are happening. So how the sediment will be deposited? Like this way, then another layer will be there. So due to the presence of this reef structure, you are having the folded structure. I'm not drawing it properly, okay? Like this. So suppose 1 year the river walk or anything, for any physical agency depositing sediments of, this is the, let's say this is sand, and this is shell has been deposited later. This is shell, then again sand has been deposited, sand layer, and after compaction you will be seeing a folded structure, and that fold is only because of the presence of this reef structure. So this can occur around a single pebble boulder or an exotic block. The fragments, and when I'm talking about a boulder or an exotic block or any existing rock body, that rock could be of tens of kilometers. It could be 10 kilometers in length. So the structure it will create, it will be havoc, it will be huge. Okay. So such folding also frequently develops in layer deposited over irregular erosional surfaces. And one more thing I didn't describe here, that the differential compaction. What do you mean by the differential compaction? So after sedimentation, that means the accumulation of sediments. After sedimentation, what happened? The compaction happened, and other chemical precipitation, cementation, these things are happened. But the main part is there is the compaction. By compaction, a sedimentary rock form. And how this compaction or this pressure you are getting? This pressure you are getting from the overlying load. So by differential compaction means not everywhere same type of compaction is happening. For this reason, what may happen is that the strata is thinnest at the crest, like this. This layer, consider this layer, others I cannot draw it properly. So consider this layer. From here you can get an idea that at the crest it will be the thinnest, and at rest of the portion or at the limbs portion it will be the thickest. Okay. So for the anticlinal structure, it could be anticlinal or it could be synclinal. So here the strata are the thinnest at the crest of the anticlines. Okay. So this will be the thinnest, and the thickness here will be better than this portion. Okay. The opposite thing happen for the synclinal condition also. If there is a basinal structure, okay, if there is a basin like structure, then there will be deposited and the folded structure will be developed. So that is also quite common, but this type of structure is generally called the supertenuous fold. Okay. Now on the basis of attitude of the fold, will be classifying the folds on the basis of the attitude. So what do you mean by attitude of the fold? Attitude means strike and dip of a plane. If I talk you about the attitude mean is called the strike and dip of a bed is called attitude. Okay. Now, so depending on the attitude of the fold, you can also classify folds into several types. Chiefly 5 types folds have been recognized on this basis. First one is the plunging fold. A plunging fold is that fold which has a axial plane or the fold axis inclined with respect to the horizontal line. If the fold axis is plunging, so what do you mean by plunge? Plunge means, suppose this is the horizontal line and there is some inclination, any linear features or anything. Okay. So if this thing happen, this angle is called the plunging angle. Okay, so this angle will give you the sense of plunging, and this inclination is called the plunging. So if your fold axis is inclined and making an angle with the horizontal line or the horizontal plane, then you will be saying that that fold is a plunging fold. Okay, so in a anticline, plunging is directed towards nose and syncline is directed away from the nose. So this structure, this folded structure is exactly look like nose, and by seeing later I will discuss how you recognize a fold in field. There you will see that this nose kind of structure is very prominent to understand the folded to understand the fold or the fold structural mapping. So in anticline, plunge is directed towards nose, and syncline it is directed away from the nose. Okay, so if there is a inclination, from the horizontal line, that's called the plunge. If fold axis is plunging, it's called the plunging fold. Same explanation. For the non-plunging fold, whatever the fold, the regular fold I was drawing from the day 1, that fold was non-plunging fold. What do you mean by non-plunging fold? When the fold axis is not plunging. So here you can see the fold axis is plunging and it's making an angle with the horizontal line. But here you can see the fold axis is horizontal. A fold plane is the horizontal. Okay, so the fold axis. Okay, so the fold axis is horizontal. If you draw a axial plane, you will get a axial plane like this. So here the fold axis is horizontal, and as it's not plunging, that's why it's called the non-plunging fold, and as it's plunging, it's called the plunging fold. As simple as it is. Now there is another type of plunging fold you can identify, that's called the W plunging fold. It kind of it may be looking like a dhol, malum hai na dhol. Okay, so if you cut the dhol in a half, it will look like that. dhol malum hai ki sab kisi ko? dhol malum hai dhol ki?
Yes sir.
So उसको अगर आधा करोगे तो जैसा दिखेगा. So my point is that in this type of fold, what happened? Two opposite plunging direction you can see. One in this direction, another one in this direction. Like this one. See here. If I take this is a axial plane. Okay. So this fold axis is dipping this direction in the front direction. This fold axis is dipping that direction. So there is a plunging. It's deviating from the horizontal line or horizontal plane, but it's plunging in different direction than the others. So fold reverses its direction of plunges within the limits of the area under consideration. Just like a top surface of a hole. That's kind of example of the W plunging fold. And the hinge line plunges in two opposite directions for obvious reason. It's plunging in the front direction, it's plunging in the back direction. So this line is dipping in layman's term, or in simple term, this line is dipping in the front direction, this line is dipping in the opposite direction. As there is double plunges are there, that's why it's called the W plunging fold. Now another type of structure you will be seeing, or another type of fold you can see under this classification, under the classification attitude of the fold. So we are discussing about the attitude of the fold, the strike and deep conditions of the fold. So depending on the attitude, I am classifying these things. And fourth type is your periclinal structure. So periclinal structure basically can be classified or can be recognized into two types. One is dome, one is basin. Dome means it's a mound-like structure. So when it's a mound-like structure, what happened? From that portion, from the center, if you do the structural mapping like this, if you do the structural mapping and it's a mound like structure or hill structure, then what will happen? This dipping will be away from the center. It's called the coaxial dip. So let me explain this. What do I mean by this? Okay, so what does this mean, this T? Okay, so this T means this is the strike direction and this is the dip direction. You know that the dip is perpendicular to the strike direction. Okay, so here you can see from the center position, the dipping case is or the strata or the bed is dipping away from the center position. Okay, just like a mound like structure, that's called the dome. If this is a crater like structure, that's called the what is called basin. Okay, so in the basin case, you can easily understand that if this is the strike direction, this is the dipping will be towards the center, and here the dipping is away from the center, right? So this dip is called the coaxial dip. This dip is called the centroversal dip. And you will find oldest strata in the core for the dome condition. For the basin case, you will find youngest strata in the core. Okay, so here upwrapped displacement of the rock you can see. In the basin case, downwrapped displacement of the rocks you can see. So dome is kind of a anticlinal uplift. Suppose a small mound is going up and it make a folded structure in the surroundings, that's called the dome. And if there is a like crater, volcanic crater is there, so if that structures, you might have heard of eye of the earth in the Sahara desert, that's basically the dome structure. Eye of the earth, have you heard anyone? Eye of Sahara, not eye of the earth, eye of Sahara, it's actually a dome structure which is quite visible from the satellites. Okay, so this is an example of dome from Utah. And so what is a coaxial dip? This type of dip is a coaxial dip. Okay, so where the dip in all direction away from the central region is called the coaxial dip. Centroversal dip is the dip in the all direction towards the central region is called the centroversal dip. Now most important part of this classification is the recline fold. So recline fold are almost similar to the recumbent fold. But what is a recumbent fold? If you recall, the recumbent folds are those which has a nearly horizontal axial surfaces like this. If the axial surface is horizontal, then it will be called as a recumbent fold. But in case of reclined fold, remember this very carefully because I will ask you about this later. I'll be presenting some photographs and I'll ask you, so be ready with that. Suppose this is the axial plane of this fold, and as you can see here that the axial plane is dipping this direction, and in the same direction the axis is also dipping. So the reclined folds are fold axis plunging down the dip of the axial surface. If I refine this thing, that hinge line you can see, the hinge line is dipping along the axial plane. That's called that type of fold is called the reclined fold. So this is an example of the reclined fold. The entire axial plane is dipping this direction, and the axis is also dipping in the same direction, or not dipping, plunging. Plunging should be the accurate word. Now, based on the interlimb angle, so what is the interlimb angle? Anyone? What do you mean by interlimb angle? What do you mean by interlimb angle?
Angle made by the tangents.
From which point I will be making the tangents? From the inflection point? From the inflection point, you remember the inflection point, right? Where the sense of curvature changes. Okay,
Yes.
that's the minimum curve point, or minimum that's the point where the curvature is minimum. That's the inflection point, and from that point you will be drawing drawing tangents, and that will be intersecting some point. So gentle fold is 180 degree to 120 degree. Okay, that's a kind of wide like structure like this. So this type of fold would be your gentle fold. If I draw this structure, so if I draw the folded structure here, yes, of course you are not understanding. Let me take it. Okay. How I can rotate it? I can. Give me a minute, okay? Yes. So I have rotated it. So what do you mean by gentle type of fold? So I'm considering that the interlimb angle is 120 degree. So if you draw it, okay, one folded structure, you got the idea, right? For the isoclinal, how I can draw it? So that could be the isoclinal. That's the isoclinal. So if I take this is kind of isoclinal. So isoclinal means when this angle is 0 degree or near to 0 degree. That's called isoclinal. So depending on the interlimb angle phi, we are classifying the fold into 5 types. Gentle fold, where the angles are in between 120 to 180. Tight fold, 0 to 30 degree, and isoclinal fold when both the limbs are parallel. When both the limbs are parallel, then I'm saying when both the limbs are parallel to each other like this, so this will not intersect at some point, or it might intersect at low angle. So that type of fold is called isoclinal fold. So what type of fold is this? This one, class? So what's the angle it's making? The interlimb angle. If you draw it, so that's the strata. If you draw the interlimb angle, then what will be? If you draw it from here,
it is very nearly 0 degree.
0 degree. So it's a isoclinal fold, very near to the 0 degree. See, in nature you will not get the actual 0 degree, but it's kind of giving you the sense that is a isoclinal fold. Now based on the depth of the axial plane, remember, so we have classified fold on the basis of what? On the basis of interlimb angle. Now I am classifying the fold on the basis of depth of the axial plane or the axial plane orientation. तुम्हारा axial plane कैसे orient कर रहा है, depending on that you are classifying the folds. So first one is the upright fold. So this is your upright fold, where you can see the axial plane is vertical. Okay, when the axial plane is almost vertical, I mean the dip could be within 80 to 90 degree, then you will be saying it's a upright fold. These are very general terms used in geology. Okay, so you should know about this, that the upright fold, upright means it's a perpendicular, the axial plane is almost perpendicular to the horizontal plane. Now steeply inclined fold could be when the dip is almost 80 to 60 degree. Then I can classify another classification, that moderately inclined fold, that dip is 30 to 60 degree. And there is another fold that's called the gently inclined fold. By seeing this photograph, I think you got the idea. Now you incline this deep axial plane to 10 degree, then you will get the gently inclined fold. Okay, fifth one is the recumbent fold. When the dip is from negligible amount to 10 degree, then you will have the recumbent fold. So where is the recumbent fold here? Where is the recumbent fold among these 5? Where is the recumbent fold? When the axial plane is at 0 degrees. If this is 90 degree, which one is the 0 degree? So A, B, C, D, E, tell me which figure is giving you the sense of recumbent fold, or which is the schematic diagram of the recumbent fold? Which one? Tell me. This one is very simple. Okay, so the axial plane ड्रॉ किया हुआ है. So recumbent fold में deep होता है 0 से 10 के अंदर, मतलब is nearly horizontal. So this one could be your recumbent fold. This one. Now another two folds diagram you can see here. That first one is the recline fold. So what is a recline fold? I just discussed in the last slide. So what do you mean by recline fold? See, these classifications are not given by me, it's given by Fleuty 1964. So he has basically classified this. So what do you mean by recline fold? Class? And another type of fold you are seeing here at the below bottom, which type of fold is that? So this is a overturned fold. I am not going to explain what is the overturned fold. Go through the materials otherwise, or go through that book, that Banger book. Okay, then only you can understand. The problem with you people are that you are not reading. These things are already discussed. So what is overturned fold, what is recline fold, I have already discussed. I am not going to explain it again. Now based on the amount of plunge of the fold axis, you can also classify depending on the Fleuty method. You can classify, and Fleuty method is very much applicable to understand which type of fold is that. Suppose you have a fold structure or fold photograph, or you did some structural mapping. From there you can understand which type of fold it could be from the Fleuty method. Okay, so depending on the plunge of the fold axis, yeah, it can be classified as subhorizontal fold, gently plunging fold, moderately plunging fold, steeply plunging fold. I'm talking about the plunge of the fold axis. Now if I talk about these two are almost same, that's why I didn't explain it in details. Now if I talk about the amount of plunge of the hinge line, now some of you might ask that, sir, hinge line could be curved, so how could you estimate the plunging? Or it could be curved, it could be have different plunging direction, it could be of different nature. So let's say I'm considering the straight line here. So hinge line can be curved or straight, or it most of the cases you will find that it inclines relative to the ground. If the horizontal fold is negligible and plunge is up to 10 degree, then for the horizontal fold the plunging is up to 10 degree. For the vertical fold the plunge is in between 80 to 90 degree. In between you have the plunging fold. depending on the hinge line. I hope you remembered what is a hinge line. Now deep of the axial surface, this is a diagram for the Fleuty method from the, and if you plot deep of the axial surface in this axis and this vertical axis, if you plot the plunge of the hinge line, then if it's a 10 degree 0 to 10, you will have the recumbent like this. Okay, so it's from the Fleuty method. And if your deep of the axial surface means axial plane, this green or green shade plane is the axial plane, this is the axial plane. Okay, so this axial plane, if it's horizontal or almost nearly horizontal, then I will be saying it's a recumbent one. Okay, if the deep of the axial plane is in between 10 to 30 degree, I have already discussed, is the gently inclined. Now if the axial plane is perpendicular to the horizontal plane or almost perpendicular to the horizontal plane, the angle is 80 to 90 degree, then I will be saying, so it's starting from the 0 degree going up to 90 degree like this, and here the plunge of the hinge line is starting from 0 degree and going up to 90 degree. So 0 to 90 degree you are having. So now tell me, it's called, what it will be called? It will be called upright. Similarly, if the plunge of the hinge line in between 80 to 90 degree, then I will be saying that fold is a vertical fold. So if I draw a folded structure, okay, and this is our axial plane, you are seeing the axial plane is vertical, and you are also seeing that the hinge line, that's the hinge line. Hinge line means maximum curvature line on the fold surface. Okay, so this hinge line H and this is the axial plane S, both are perpendicular to the horizontal. Okay, so this type of fold is called the vertical fold, or it can be called as, depending on the axial surface orientation, what you can call it. As the axial surface is or axial plane is vertical, what you can call it? This fold. What you will be calling this fold? So it's a vertical fold, and it will be also which one?
Upright fold.
Yes, it's also upright fold. So your section B, one student from section B, he was asking that is it possible to have the upright and vertical fold together, and it's quite possible. So this is, from this diagram you can see that 90-90, that's the structure. Okay, now there is another fold drawn here, that's called the recline fold. So what do you mean by recline fold? I have discussed, where the axial surface or the axial plane and the hinge line, for now let's consider it's a hinge line, straight hinge line, are in the same direction. So these are dipping in the same direction. So in which point you will have that thing, at which point you will obtain? At this point and again at this point. So here you can see the plunging is 60 degree and dipping is also 60 degree. So then it's a reclined. Here also you will be seeing that plunging of the hinge line is 30 degree and dipping of the axial plane is 30 degree. So here also you can get one reclined fold structure. Okay. Now another example has been presented here, that you can see that if the plunge of the hinge line is 30 degree, see, plunge of the hinge line is 30 degree and deep of the axial surface is 60 degree, then the fold will look like this. So the fold or the classical one I used to draw, or I am drawing from the class 1, that I was drawing that upright fold. Okay, upright horizontal fold. So if I if I want to specify it on the basis of these two parameters, then I will be saying it's a upright horizontal fold. Because the hinge line is horizontal. Why upright? Because the axial plane is perpendicular to the horizontal plane. That's right, upright. Now, based on the mechanism of folding, the fold can be classified into mainly three types. First one is the drag fold. So to understand drag fold, let us consider two things. That let us consider there is a horizontal strata, okay, and in between where this layer number 1, this is layer number 3, and this is our layer number 2, okay. So this is 1, 2 and 3, and I am assuming layer 3 is incompetent comparing to layer 1 and layer 2. Okay. So what will happen? If you give lateral pressure to create a fold, then what will happen? The folded part, due to the presence of the lateral pressure, the competent layer, competent means this layer are the hard rock layer, okay, and incompetent layers means these are the soft layers, okay. So drag during folding, when a bedding plane slip occurs between the competent and the incompetent layer, then you will find after giving the lateral pressure, because it can, this yellow zone or yellow layer can be modified into the fold in very easy way, because it's a soft thing, okay. So competent layer will folded like this, incompetent layer, so it might be folding like this, the competent layer. So it will make a nice fold, and the incompetent layer, the yellow layer, it will be looking like it will create some second order folding like this, some minor folding you can see, okay, and that's the incompetent layer and that's the competent layer. This type of fold is called the drag fold. Okay. So in a very large number of cases, direction and amount of the pitch of the drag fold is the same as that of the measure fold. Other than drag fold, another type of fold is there, depending on the mechanism or on the basis of mechanism of folding you can classify. That's called the flexural fold, and this is also very important. What is a flexural fold? Similar kind of competent incompetent funda is there. So let's discuss this flexural fold. So in the flexural fold, what happened? Competent layers do not change their thickness because they are competent. That's the characteristics of competent layer. It do not change their thickness. What happened? Incompetent layer modified themselves. Incompetent layers are marked by cleavage sets. A several plane of weaknesses will be developed and nearly parallel to the fold axial surface. So flexural folds can be subdivided into two types: flexural slip folds and flexural flow folds. In flexural slip folds, there are displacement along bending surfaces much like the bending of a telephone directory probe. So if you are bending a thick book, okay, so suppose 1000 pages book you are bending, and there would be a displacement along the bending surfaces like this way. There will be a displacement in the bedding surfaces. In the competent strata, incompetent strata mein kya hoga? What will happen in the incompetent strata? It will create a set of cleavages. Cleavages means the weak plane of cleavages are the weak planes. Okay, so I will discuss it in details later when I will be discussing joints. So these slips are created along the fold limbs and approach zero along the fold hinge. So whatever the slip you will be seeing, slip means the fold it's supposed to make, it will be changing, and that offset you will be getting, and it will be greatest, it will be larger along the fold limbs and approach 0 along the fold hinge. हिंज के साइड में वो 0 हो जाएगा स्लिप, जितना स्लिप होना चाहिए था. एंड let me show you actually. From the limbs, the incompetent layer or incompetent material will move towards the hinge, and by this way it will make the hinge thicker comparing to the limbs. So limbs will be thinner because the material from the limbs will go to the hinge portion, and it will create a flexural flow folds. So flexural flow produces similar folds in the weak layers. I have discussed what is a similar fold, very first slide. Now another type of mechanism or another type of fold you can classify depending on the mechanism, that is shear fold. Shearing, I hope you are familiar with. Okay, so two opposite forces you are giving, and some shear deformation are happening. So this is the initial stage. Later you will find like this. So shear fold, it is also known as the slip folding or the Gliedwetter folding. It results from the minute displacement along closely spaced fracture, and each fracture is actually small fold, and the blocks on either side of it moved upward or progressively. See here, the folded structure will move like this, kind of overturned fold. You will be seeing that fold is called the shear fold. It also referred to as slip folding. Okay. So shear fold involves shear along the planes that are oriented approximately parallel to the axial plane of the fold structure, and these planes facilitate high angle reverse slip leading. So there will be shearing, and this type of structure will be developed. So that's it for today. Okay.